Welcome, thanks for joining me. This presentation is on thermal conductivity in materials, and I'm Mr. B. Let's get right into it. Let's get some background information here real quick. Thermal conductivity is defined as the ability of a material to conduct heat from its one side to the other. Remember, energy transfers from wherever you have a higher temperature, that's where there's more kinetic energy in the particles, to the lower temperature areas. Everything wants to become into an equilibrium state, so they're going to share that energy, and it goes from the high temperature areas to the lower temperature areas. I have a table here of a property called thermal conductivity, and you can see in these materials everything from air up to diamond, and there's many more besides this here that I'm showing, but air we can see is 0.02, very low, and diamond is upwards of 1,000. So when you go to the high end, those are called thermal conductors. They transfer the energy very quickly. The lower end, those are thermal insulators. They transfer energy slower. So those are going to be generally a lot over here on this side, everything air to glass, and maybe even brick and rock. They transfer energy slower in most senses. I've created a couple labs. Some of these I've found from other sources, and I've created my own out of them. So what I'm going to be presenting is how these are run and some results that you can get from them. So first we have a spoon and butter in hot water lab, and then we are going to look at using different cups of materials along with an ice cube in a melting ice cube lab. So let's look at our first lab here, which was a spoon and butter hot water on this neck. Hi there, I'm Mr. Weringer. I'm in the lab here in the classroom. We're going to be doing this conductivity of materials test, and what I have here is a simple setup. I have beakers set up out here. I have some hot water. I set it to get close to boiling. I'll actually restart it. This here is a hot water maker. It can make hot water in large amounts really fast. So we're going to get it rolling, boiling here. You can see bubbles already forming. We have some butter because we're going to put it on the end of our spoon handles. And then I also have a thermal imaging camera that I can then attach to my phone device or iPad, and we can see thermal images, which will be really neat for students to use. But let's get our setup going here. What we would do is we pour water in each of our beakers, and then we have our different samples of materials. I have a wood spoon, I have a stainless steel spoon, and you'll know stainless steel in some cases is magnetic, so you can try a magnet on that, or it is written on the back as being stainless steel. I have aluminum. Now I couldn't find an aluminum spoon. I found this aluminum pie serving utensil essentially. It is a little bit longer and thicker handle, which may change our results, but that is not going to be too big of a change. We should see good results still with this here one. We have a copper spoon. You can find these online. They are pricey, $10 to $20 a piece, but for this experiment, it's really neat to see copper and how thermal conductivity results through it, and plastic for this here testing plastic spoon. So I'm going to put a little bit of butter on the end of each handle. I'll show you real close. It is not a lot, just a little bit. You would pour your very hot water, you want very hot water, into each glass. And then try to put all your spoons, utensils into the glasses. The reason I have the larger one here is to hold this larger aluminum, basically pie serving utensil that I found so that the glass wouldn't tip over. But we should find fairly good results with this test, even though it is slightly different size. You'll put them all in. And from here, you just watch which butter melts first, second, third, and so on. And that's where the thermal imaging camera will be really neat for students to see. You'll also want to note that I am trying to get the handle away from any convection that's coming up out of the hot water. So we're trying to, right here you can see the butter just melted off of the copper. We're trying to watch and learn about conductivity through material. So we're trying to get the butter sample away from any hot air, hot steam rising off of our boiling water. So trying to reduce that effect of the convection and more look for testing the conduction through our different materials. So that video was how I set up, and now we are going to watch through the thermal imaging camera. And this I have sped up so that we can get through it all. Alright, so here you see I'm pouring the water in. Obviously the middle one is a double glass, that's why you don't see it as well in the thermal imaging camera. And it happened really quick. The copper one was actually 20 seconds. That was very fast, it appeared. You can see how the butter melted down, right down that spoon. So the next one will be the aluminum coming up. And this is sped up, this video, but the aluminum occurred at about 3.5 minutes. That'll be right there in the center. You're going to see how the butter starts to get warmer in temperature. What's really cool, the students, as we did this in classes, they just loved how you could put your hand in front of the thermal imaging camera and do all kinds of stuff. They just loved seeing this, and look at that butter warm up, and it melts down on the center there on the aluminum, melted down. And then our stainless steel occurred at 8 minutes. You can see it's warming up there on the end, on the left end here of your screen. I have that video sped up quickly here so we can get through this. Obviously, as the test was occurring, lots of time to talk with students and anyone in attendance watching this, so we could all get a better understanding of what's occurring. You can see that's glowing more, and it's melting and running down the handle there. So the butter on the wood spoon and plastic did not melt in 20 minutes time, and by then the water temperature had dropped from about, let's say, 90 degrees Celsius when I poured it to about 60 degrees Celsius, and it was losing energy to the air and atmosphere around. So the plastic and wood was, those butter samples were not going to be melting in this testing, but it shows that they are insulators, right? So let's take it further. Take it further. What I'm saying here is, now that you've seen different materials, what would you choose for your tray of butter? Obviously here you see something that's made of a plastic or maybe porcelain, which are insulators, right? And we often use stainless steel utensils and cutlery. But what if you could get a copper knife? Would you rather use a copper knife because maybe it could warm up the butter as you slice it and spread it on? Wouldn't that be something? Along with that, I had thought of the idea, what about some cold ice cream, right? Dairy products. And so here you can see this is stainless steel, these first two, and then over here on the right, that's actually aluminum. And I had tested this out myself at home, and aluminum versus stainless steel. Now, it was hard to kind of just feel the scooper if it was easier with the aluminum, but I definitely felt my hand was feeling cold, and that's because the energy from my hand going into the handle to the ice cream. So definitely there was energy transfer as I was scooping a couple bowls for my daughters as we were getting some ice cream and testing this out at home. So that's something fun to do on the side after you try the butter lab. So let's look at our next one.
Here we have a setup for testing thermal conductivity using some ice and different materials in cups. So I have a copper cup. Make sure if you do this, you have a copper cup. It's copper inside, outside. It's 100% copper, or it's listed at least 99% copper. I have aluminum cup. They actually make disposable aluminum cups, just like plastic cups. This here is aluminum. You can find online or in your stores. We have foam, plastic, and I have a glass beaker. You could use a glass at home, glass beaker, some type of glass. As for plastic, I've chosen to use a single plastic cup and a double plastic cup, with the idea that you have now air in there as a barrier, which could be an insulation barrier along with your plastic. It'd be neat to see if you can compare single wall compared to double wall plastic, if there's any difference in melting your ice. All you're going to do is have your students select ice cubes that are similar size and drop them into each cup and start a timer. You may want to have them document when the ice cube starts melting and completes melting in each cup. It would be neat to see how each one starts melting at a different time, and maybe the melting process is really quick in one compared to another. Take note that in a couple of the cups, especially the conductive materials, metals, they will melt fairly quickly as compared to the foam and glass and plastic may take quite a bit longer. I have conducted this experiment for ranges of 20 minutes to an hour on my own in classes, and it gives enough of a result that you will see some really unique differences between materials.
So now I'm going to be playing a video of my thermal imaging camera, but again, I've sped it up, so we're going to see what it looks like here. All right, so you can see I put the ice cubes in, and it shows dark color because it's cold in the cups, right? You can see the top right is a copper one, and this is sped up, and I think I did it about 16 times. Pretty fast though. And you can see how in the copper cup it's getting cold in there, right? Or the energy is going in there and melting that ice cube. And that ice cube is slowly melting there. Slowly I say now, but actually it was fairly fast compared to other ones, right? On the bottom right is the aluminum cup, which was second quickest in melting. There you go, the copper cup. That ice cube is gone, melted. Look at how also the cup was cold, dark color, and it's starting to lighten up. That's because it's getting energy from its surrounding atmosphere, and it's becoming basically the ambient temperature of the table that's there, which is listed up top around 22 to 23 degrees Celsius. It's almost disappearing from sight because it's becoming ambient temperature. It's taken on the energy from the table and the air around it. Down on the bottom right, you can see the aluminum cup. The aluminum cup there, that ice cube is melting really well, quickly. And I would say from my experimentation, the third one was the glass cup here on the top left. Down on the bottom right, that ice cube is melted and gone, and you can see that cup also now changing its color to become more like the ambient temperature around it in the table. It's just so neat to see this with a thermal imaging camera. Another thing you can ask students, hey, they could pick up the cup and feel the table underneath it, because the table is going to be cold, meaning there was energy coming through the table into the cup, through the cup into the ice cube, right? But just warn them that they shouldn't be touching the cups too much, otherwise they're adding energy to the system through their hands and fingers, right? And so that's where our video stops. I stopped it there. But you can see how the glass one was the next one, the third quickest. And then after that, if I recall, it was the single plastic cup, and then the double plastic cup and the styrofoam cup in the center. Both of those, they were holding the ice probably close to nearly an hour. They're doing really well by insulating it, right? So now what I would ask students to do is to draw an energy diagram. So they're just going to draw the setup or the system. We have obviously a table, and we have, I'm just going to draw oversized cup and ice cube like that. Nothing fancy, just get the point across. So where is the energy going, and from what material to what material, and what's all going on here? Well, to start, we have air surrounding everything, and that is at an ambient temp, roughly 20 degrees Celsius, which might be about 68 to 70 degrees Fahrenheit. Okay, so the air is that temperature, so is the table, so is the cup. Okay, but the ice cube is, it's less than 0 degrees Celsius or 32 degrees Fahrenheit, right? So energy goes from the high temps to the low temps. It is going to be traveling into that ice cube. But how? How does it do it? Well, it does somewhat through the air, but we on this test we're looking for the conduction, which is direct contact, which is the cup bottom and also the table. So the table to the cup to the ice cube, okay? And also it will travel through the material of the cup. So during the test, you could have students touching the edges of the cup to see if it feels cold. And that's because energy is being drawn through the material all the way down to the ice cube. They could also pick up the cup briefly just to touch the table and see that the table feels cold. And that's because energy was being drawn through the table, through the cup, into the ice cube in this system. And so this is a neat way to have students display their understanding of what's going on in this system. So here's something else. Take it further. Now you tell students, okay, we just seen how to melt ice quickly. What about making ice? What are some options to maybe make ice, and how could you maybe make ice quicker? Well, obviously a lot of people know about these plastic trays, right? They're cheap. They come in freezers sometimes, or you buy them and you can bend them and, well, snap out the ice cubes. Okay, you can buy these silicone ones. They make many in different nice, neat shapes. You can make ones, if you're handy, you could actually make your own silicone ice cube trays. And there actually are stainless steel ones. Now these get expensive. I've seen some online for going for $40 for a set like this. And then with this, the instructions that I saw online said that once you take it out of the freezer, you need to actually put the tray in like a plate of water so that it can start a little bit of melting process so you can get the ice cubes out of the tray easier. Which leads me to what an ice maker in a freezer actually does. So the thing is, we just saw in our experiment, as you melt ice, you can melt it quicker with a metal that conducts the energy. You can also freeze ice quicker with a metal. Now here you see plastic all around, but actually inside that's a metal tray. So what happens is there is a timer and some gears over here, and it turns, and first it's going to turn for a certain amount of time to pour in water, fill up the tray, then it freezes for about an hour. There's a time that's set on these. Then the timer clicks and it's going to release electricity through wires, copper wires that run alongside of it that warm it up just for about a minute, enough to start melting that ice. Okay? It starts melting the ice, and then these here, what looks like plastic fingers, they can move and scoop out the ice and drop it into the bucket. And so that's the system that's used in an ice maker. All because they're using a metal tray to make ice quicker. Now, just note that the metal tray is sometimes coated with a non-stick coating on the inside, but the overall concept is having a metal conductive material so that energy can transfer and you can make ice quicker. Well, thanks for joining me. That's all I have for you today on thermal conductivity materials. Please like and subscribe. Have an awesome day.